All right, it has kicked me out, but we're going to do a second video. It's easier, I think, to do that than to kind of restart, try to say what I said again. I hate trying to do that. Okay, so got to share this back again. I think I had too many windows going at one time. All right, so classic experimental design. In this classic experimental design, you're going to have a pre-test, post-test, randomized control group design. It's a lot. It's a mouthful, but it's really simple when you break it down to its basics. Okay, and so that's what we're going to do. When we do this pre-test, post-test, randomized control group design, it includes all the desired factors. It has random assignment. Random assignment means you're randomly assigning people to conditions, which means you can't have, I'm going to put all the men in one condition, all the women in another condition, or I'm going to, pick the first 10 people and put them in the condition A and take the next 10 people and put them in the condition B. That is not random. Random is putting everybody in a hat, and everybody has an equal chance of being in one group or the other. And then you have this control group and an experimental group, and then you take measures both before and after the treatment. So pretty simple, experimental design. Sorry, I got a text there. In terms of it's set up, and you can do this with more complex variables or simple variables. But you have an experimental group, right? So say we're doing this with our two study methods, right? Or say we're doing it with a study method. In the experimental group, you're teaching them a new study method. You give a pretest, which means you assess their ability to remember material. Then you do the experimental treatment. Hey, we're going to have you study in two 30-minute slots of time as opposed to an hour slot time. And then you're going to do a post-test. That post-test is to assess the impact of what has occurred with that group. You then have a control group, which is your comparison group, where you do the same thing. You give them a pretest, see where they're at, give the control conditions, so study to 60 minutes straight, and then you assess the post-test. And then you are comparing these two things. You're comparing the post-tests. The good news is you can also compare within. Did they change from pre to post, right? So you might have them study the way they normally do and assess whether this change in studying improved their study methods, and do the same down here. Have them study the way they normally do and have them study 60 minutes and then assess that. And so you're comparing both within and between two different conditions as you go through. And that's kind of the classic experimental design. And it works pretty well because it's easy to assign participants into random groups. It's controlled. You have very few extraneous variables, and so it works pretty well. In that classic design, if the experimental group makes greater gains from the pretest to the post-test than the control group, and if the two groups have been treated the same in all respects, and this is important, that they've been treated the same in all respects, except for the experimental condition, then the difference is attributable to the two causes, the treatment and then random errors. And there's always going to be random errors, right? So someone is not going to perform perfectly every time. You're going to have changes in the pretest to the post-test. You're going to have changes between groups just from, change over time. But if the change is bigger, you're going to have that treatment change as well. And that's why we do experiments, so that we can control those situations. That classic design representation can be simplified by using symbols, where R is a random assignment to groups, O is the observation or measurement, whether pre-test or post-test, and then X is the experimental treatment. So if you set that up, you have a classic design here where you have randomize. You do an observation beforehand. You do the experimental condition, which means here you're doing the experimental condition. This one, there's no condition, so you don't tell them anything. You just there's no treatment, and then you're comparing here at the end. So the design itself looks like this. And so oftentimes when we are writing up design elements, it'll look like this. So we're setting it up in almost this pictogram, football play kind of way. So it's a little bit easier to make sense out of those variables. And so we're going to do that as we kind of go through with all these other types of variables. One of the biggest and most important aspects of an experiment is random selection. Random selection to an experiment and control group assures that the researchers have assigned people in a way that is not biased, right? We are shooting for non-biased assignment. Bias is what kills experiments. If you have bias in your experiment, you haven't done it correctly and you cannot interpret your results. So you always try to minimize the amount of bias you're introducing. Now, sometimes it's not possible to reduce all bias, but you can reduce it significantly and in a way that it doesn't destroy your experiment. So the pretest offers the advantage of permitting the researcher to determine how much change has occurred in the experiment. So that's what we do, a pretest and a post-test. What happened between this point in time and this second point in time? Was it an improvement? And what was that improvement? Other times in an experiment, we have a post-test only randomized control group design. In this situation, it becomes necessary to, if I don't delete these, it crashes my computer, I've learned. So in the post-test only, sometimes you can't provide an experimental condition to someone because it changes those people, right? So if you do a pretest, it warns them what they're supposed to be doing, and it changes what they're going to do at the end, and it ruins your experiment. So you can't do that. So pretests can sensitize the participants by giving them the pretest. It gives them a sample of what they're going to have to do, and they learn from that. People are pretty good at learning from those situations, and that's called a pretest sensitization or reactive effect of testing. So just giving them the materials makes them aware of what they're expected to do. So to overcome that effect, experiments are given without a pretest, oftentimes as shown in this design, where you randomly assign people to two groups, then you just examine the effect of the experimental group and no experimental condition here, and then you make an observation at the end. This is the one that I typically use in most of my experiments, is this post-test only randomized control. So you're not doing a pretest, you're just saying, okay, I'm going to give these two experimental conditions and see the impact on the groups after I do that condition. And it is the random assignment here that makes the groups comparable, not the pretest. It just provides that base measure of the control group, and the fact that they're randomizing it provides all the assurance that you're doing and can make causal statements at that point. There's a whole bunch of other designs, and I don't want to sometimes you get in the weeds with these things. You can take yourself down the rabbit hole and do a million of them, but I'll talk about a couple of them. One is the Solomon randomized four-group design. In this research design combines kind of 1 and 2. It has 4 rows because it has 4 groups of participants, each with slightly different process. It's kind of like conducting 2 experiments. So you have a random group here. You do the pretest on these individuals, then you do the experiment, and then you observe again. This is the first example of what we did, right? Pretest, post-test. Then you do the whole thing again, except this time you only do the randomization and the experimental condition, and then you include the observation at the end. You are able to determine what the effect of the pretest is on those individuals. If there's a bigger change here than here, then you know the pretest was having an effect, and the pretest was driving some of those initial results. But you need a lot of people, right? Think of it this way. Every row is a group of participants that you need. You need 15 to 20 people on average per group when you're trying to make comparisons among those groups. That's a bare minimum. Ideally, you want more, but on a bare minimum, you want 15 or 20. So if you're only doing one condition, then it's 15 and 15, so that's 30. If you add 2 more rows, you're going to double your experimental size, and that sometimes becomes cumbersome as part of that process. All three of these are what we call true experimental designs. They're true experimental designs because they all have one thing in common. They have random assignment. Random assignment is the key to a true experiment. Without random design, without random assignment, you do not have a true experimental design. That being said, a lot of psychology uses non-true experimental designs, pseudo-experimental, quasi-experimental. There's a lot of different terms for it. We're going to talk about those next. It's because a lot of variables you can't randomly assign. You can't randomly assign people to gender. You can't randomly assign people to have been a victim of a crime. And so those are difficult to study, but you can study them in a quasi-experimental way, and we'll talk about those here in a second. So what are our threats to internal validity? Internal validity, let me get rid of that stuff again. Internal validity means the internal structure of the experiment. So if you're carrying out an experiment and you observe major changes in participants' behavior, so you do this study technique and you say, hey, my technique of using 2 30-minute blocks of studying way improves people's ability to retain information. This can be explained best if there are no threats to internal validity, okay? And those threats to internal validity, right here is what we're talking about, means that you have a poorly designed experiment with no control group, is one of those threats. So imagine a poorly designed experiment, no control group. If you see changes between this point and this point, was it actually the experimental design or was it something else? You don't know. People just change over time anyways. Is it just giving them time? Is it something else that was a part of this experiment that caused this difference? And so if the researcher finds an increase of 9 points in some self-concept from pre-test to post-test, or in the score from pre-test to post-test, did the treatment cause the increase? Perhaps it was some internal threat, something called history, for example, just the fact that people change over time. That is an internal validity question. Threats to internal validity are threats that harm your ability to make decisions based on your experimental design. So if you have poor internal validity, you have poor experimental design, and you can't make decisions or conclusions based on that experimental design. History is one of those threats. So there might be another environmental influence between the pre and the post-test that affected participants' responses. If you're doing a self-concept study, that's the one they use in the book. Imagine that the person fell in love with someone between the pre and the post-test. Well, that might influence their ratings of self-concept. In our experiment, between the pre and the post-test, if they're learning a new study technique, what happens if they're also taking other classes on the subject matter? They're learning things that are not specifically encoded within your study. And if that's the case, then maybe it's just the fact that they're being exposed to more stuff that's helping them do better between the pre and the post-test, and has nothing to do with the amount of time they're studying. Other threats to internal validity is maturation. People change between measures. They become wiser, they become older, they become smarter. Instrumentation. The measurement procedure might change from pre-test to post-test. If you change even minor things, you might cause an effect. Testing. The pre-test might have an effect on post-test performance. Hey, here's a test and how I set up my test. I'm going to test you on it, and then I give you a post-test, and hey, you did better. Are you doing better because of my technique? Or are you doing better because now you know what my tests are like? Both of those are relevant. Those are important, relevant things. And then statistical regression. If participants were selected based on extreme scores, the post-test score is likely to be closer to the average based purely on measurement reliability. People tend to regress towards the mean, right? If you think of a normal curve here and the mean is here, if you have people in the outliers on one measure, they tend to move towards the middle the next time. They don't get further extreme as you go on with experiments. They tend to move towards that middle mean point. So it's a regression towards the mean, that's statistical regression, which means you may have no effect when there actually is one, or maybe eliminating an effect that could exist. Other threats, Selection is a threat when random design is not used, leading the researcher to use intact groups, which are previously existing groups. When you do that, selection can interact with all those internal validity threats. So for example, having everybody from a class participate in a research study. So let's say I want to do this experiment. And in this group, I use my class 1, and this one I do class 2. You can't really see those numbers, but 1 and 2. I now have an intact selection group. Everybody here is selected to be in that group. Everyone here is selected to be in that group. My differences between the two situations may not be the technique. It may be the fact that people selected to be in group 1 or group 2. And that causes problems. Or the fact that this is an intact group and this is an intact group, and they have different effects on them. Mortality is another threat. Mortality is when people drop out. It refers specifically to people, dying as part of a research study, but it also means people drop out. Sometimes if you have a study between pre-test and post-test, not everyone wants to keep doing the study, so they drop out and they stop being a participant in that research. We might have a high dropout rate for certain groups. So the group that has the experimental condition are maybe being asked to do more. If they're asked to do more, they may be less likely to want to continue, and you're going to have a higher dropout. And that's a mortality rate that causes effects as part of the design. Internal and external validity should be evaluated and treated independently. Internal validity, like we were just talking about, is the treatment in this particular case. So it's this study. What's happening in this study? What are we doing was part of this design? You can offer potential alternative explanations for the observed changes with internal validity issues. External validity is different. External validity is to whom, under, and what circumstances can the results be generalized. So this is more about generalization. So at the end of the study, who can you generalize your results to? Who can you say, hey, this is these effects will happen with college-age students. If all I use is college students, then my external validity is towards college students. I cannot generalize to, high school students or to grade school students because I did not study them. And so external validity relates to who you can generalize to. And so problems with external validity can also occur as part of your experiment. So threats to external validity, we'll look at those, include things like, again, selection bias. Oh, dang it. My highlighter disappeared on me, and my color did. So selection bias is one of those threats to external validity. And this is the interaction between selection and the experimental variable. If a sample is biased, the ability to generalize is greatly limited. If you have a problem with your sample, you have a problem with your study. You can't generalize those results, and creates problems. There's also reactive effects. The experimental setting may differ significantly from natural settings. So you bring people into the computer lab to have them study as part of a test because that's where you're doing your study. Just being in that lab environment may change their reactions. When you study children within a play environment, all of a sudden you take them away from their normal play environment, you put them in a laboratory play environment, they may act differently. That is reactive effects to that experimental arrangements. People are nervous when they come into something new, and it affects how they're going to respond. So maybe they won't be as bold, maybe they won't be as obvious about their effects in that new environment. But you can improve that by giving people time to acclimate, to give them pre-tests, to get them comfortable with the situation. And oftentimes that's what researchers will do. There's also reactive effects of testing. That's that pre-test sensitization. The pre-test may influence the participant's response to the experimental treatment. And then there's multiple treatment interference. If a group is given more than one treatment, it can have effects because can you really separate out and predict that only one of these things is causing something else? All of those are threats to external validity. So taking what you found here and generalizing to outside that research study. And that's an important part of what you're doing, right? We are doing research not to just demonstrate, hey, we have an effect here, but then to say, hey, it means this bigger picture is also relevant and important. There are also some pre-experimental designs. These are designs that are called pre-experimental because they lack those necessary ingredients to be specifically quasi-experimental, which is what we're going to cover next. Or they lack the things to be true experiments. And so they have poor internal validity. And they have limited value, but a lot of times they're good for pilot studies. A lot of times when you're doing research, you set up a pilot study to run through all the procedures. And the reason that you do that is that if you don't, you could seriously impact your actual experiment, right? So if you do the experiment wrong, if you go through the wrong procedures, you're introducing those errors that we just talked about that are going to harm your internal validity. So you want to run through these things. And so sometimes you will, in a pre-experiment design, you'll do a one group pre-test, post-test. You're just going to run through it. You're going to assess the problems that might occur with all internal validity, but you're going to assess, can I get the pre-test, post-test observation done? There's a one-shot case study. This often works for testing learning, but you can't necessarily answer causal questions. So here you are giving them, there's no pre-test, right? And you're just observing them at the end. You're giving the experimental condition and observing them to see what happens. And then there's a static group comparison. Like the others, there's no random assignment. And this design has intact groups. So that's why we have this thing here. So you have group here, and therefore there's internal validity issues which have problems with making causal statements. But they're often the precursors to research. Not all research happens at the true experimental level the first time it's done. A lot of times it's done in this pre-experimental ways to make sure everything is trying to jiving and making sense and working before you go through with the full experiment, because it's a lot of work to organize an experiment. Quasi-experimental groups provide an intermediate spot between pre-experiments and true experiments because they recognize that random selection is not always possible. Say you were interested in studying the impact of a home environment on children. Well, you cannot take children, and randomly assign them to different homes, right? I'm not going to say, I'm going to take your child, I'm going to put it in this other home, and I'm going to see how that affects them. Not possible, right? It's unethical. There's a lot of reasons that you can't do that. It's just plain wrong. But random selection is not possible, so you can't randomly assign people to those groups. So you set up a study where you study those groups as they already pre-exist, right? So design 7 is a non-equivalent control group design. This is widely used with 2 intact groups. It is still subject to internal threats of mortality, selection, and threat, but it allows a limited comparison of causal effects, right? There's no random assignment, so there's no R in the beginning. But researchers often use sample matching in place of random selection to increase internal validity. So you have an observation, a pre-test, you do this experimental condition, and then you do an observation at the end, the post-test. And the other group, so this might be class 1, classroom 1, my stats class. This one might be my physio class. And so this one, I give them an observation. I don't do experimental condition, then I observe them at the end. And then I try to see if there's any differences. Because I'm not randomly assigning them, what I might try to do is do sample matching. So I want to try to make sure that I have the same number of men here as I do here. I might look at other demographics, socioeconomic status, socio-demographic things, education, all those things that might potentially have a difference between these two groups that could cause an effect. And they're quasi-experimental because we can't randomly assign people. Pre-existing groups are often male and female. We do that. I do that a ton in my research. I study sexual assault. So a lot of my research is gender research. I can't assign people to gender. So it's quasi-experimental by design. That does not mean that I don't determine causal effects. It just means you have to set up the study more carefully, and you're limited in what you can say because of those effects. But that's not necessarily a bad thing. It's just a different thing. There's also equivalent time samples. So this design only has one group, and then the treatment conditions are altered randomly by altering the X. So there's treatment condition and control conditions and so on. This has one group serve as both the control and the experiment. So you do the experiment, you do the control, do an observation, do the experiment, do the observation, do the control, do the observation, do the experiment, do the observation. So you're going back and forth between these two groups. The advantage is that matching in the condition is identical because it's the same group. This group here is this group here. It's the same. The disadvantage is the likelihood of multiple treatment interference because they're getting the treatment here, they're getting a treatment here, they're getting a treatment here, they're getting a treatment here. That might have an effect. So it depends on the type of study you're doing as to whether that works or not. A lot of experiments come down to whether there are confounds in the experiments. Confounds is an extra variable that creates confusion regarding the explanation for a given difference. So, going back to the study technique example that I've been using. You have study group 1, 60 minutes. Study group 2, 30 minutes, a break, 30 minutes. Well, if I have all the men in one condition and all the women in the other one, I've created a confound because now is it gender or is it study time? If I have one group study in the morning and the other one at night, is it time of studying or is it the study technique? And so anytime you cannot distinguish the impact of a variable on your experimental and your control conditions, you've created a confound. And these are the things that you look for a lot when you're designing a study because these destroy a study immediately. If there's a confound, you can't disentangle it and the study becomes pretty much useless. One of the classic examples is the Hawthorne effect. It's also called the attention effect. It's named because it was originally discovered at the Hawthorne plant of Western Electric. The study measured whether worker productivity went up if lighting was increased. So worker productivity and lighting. So, hey, if we increase our lighting, is this going to increase productivity? Well, it did. When they turned the lights down, it also went up. Well, that doesn't tell us much, right? So it actually went up in both conditions. So what is going on? It turned out that the effect was not the lighting, but the act of being observed. So all of a sudden now they're like, hey, we're going to watch you work. We're going to turn the lights up or we're going to turn the lights down. Well, in both situations, they're being observed. So the confound is observation. So they felt like they were being observed, and so they worked a little harder, increasing their productivity. It had nothing to do with the lighting. And so observation sometimes has an impact. There's also a John Henry effect, which is a similar effect in which the control group becomes aware of its inferior status and responds by trying to outperform the experimental group. So it's like, hey, I'm going to work twice as hard because I am better than the experimental group. I'm going to get it done. And if they know that, then they can ruin the experiment, which is oftentimes, well, when we randomly assign people to groups, we do not tell them, hey, you're the control group. We don't really need you to try. You try to keep that information blind to the participant. Ideally, you also keep it blind to the experimenter, so we do not have any observation effects on our end. So if we know which group is better and which group is supposed to do better, we can also influence the results by saying, I'm going to spend a little bit more time with these people. I'm going to help them along a little bit more, and you can have an effect that way as well. Confounding in experiments, the placebo effect. Participants are given an inactive treatment. Individuals who are given a placebo tend to improve simply because they are being treated. That's the placebo effect, right? Placebo effects are real. That's what I want you to realize. Placebo effects are real. They're not fake effects. They actually do exist statistically and experimentally. There are changes between the pre and the post, right? What are those changes from? Being observed, doing the procedures, whatever it is, they are mentally causing these changes. There's blind and double-blind procedures. Blind procedures, which is what I just said, participants do not know which treatment they got. In a double-blind, neither does the researcher. And that's actually the best ideal because that way we cannot influence the experiment as researchers. Then there's demand characteristics. So these are cues that let participants know what the expected outcome of an experiment is. So, hey, I'm going to have you study this new technique, and I let it slip it's easy to figure out that, hey, the 30-minute version is supposed to be the better study technique. So maybe they try a little harder because they know it's supposed to be better. And so they may begin to act in a way they believe is what is expected of them, and that skews the results. All of this makes studying research difficult because there's confounding variables, there's internal validity, there's external validity, there's causal effects, there's different techniques for manipulating variables. We haven't even got to the point of discussing how you manipulate variables and all the decisions that have to go into that yet. But it really highlights to me the nature of having to be aware of these things and then to plan your experiment from start to finish. When you say an experiment, there's been a lot of effort put into making sure it works from beginning to end. You don't just say, hey, I'm going to test this group versus this group and let it go and see what happens. You're thinking about everything that's associated with those two groups. Is it the time of day? How do I avoid demand effects? Do I need a placebo test? Do I need the blind and double blind? You're considering all these things, and at the end, it comes across as a very simple experiment. Do A, do B, see if there's a difference. But in reality, there's a lot more that goes behind the scenes. So this is the summary. I'm not going to spend a lot of time on that, but I hope this gives you a little bit of a window into designing experimental research. We're going to talk a little bit more about this when we get into t-tests and ANOVAs, because those are based on groups of people that are being compared, and those are the statistics used to analyze these types of studies. So I think that is everything for right now. Make sure you do the homework on these sections. Those will be posted for the next round of homework. All right. Have a good day, guys. And I'll be back with part 2. This is actually part 2, so a part 3 and part 4 probably for the statistics portion.